Hi, I'm Shiv. In this module, I'm going to explain the VLSI design flow. As a chip designer, we design different kinds of chips like smartphone SoCs, IoT chips, and we design various kinds of chips for different kinds of applications like space, defense, and consumer. You think about smartphone SoC. They are very complex. For example, A17. A17 demands more than 19 billion transistors, and it was fabricated using 3nm technology. Here, technology is very important. We want to make sure that the transistor size is very small so that we would be able to pack more and more transistors as part of the chip. Obviously, we prefer ASIC, application-specific integrated circuit. Also, it could be based on full custom design. Here, the technology is very new, 3nm. So we might not be able to find any standard library. This is called full custom design. What it means is basically we design the transistor itself. We make sure that the channel size is 3nm. And we create the cell library. And we make use of the transistor cell library and then we design the layout. This is called full custom design. Let's say we go with something like existing technology and that has been used by many chip designers, and there are vendors, they can provide standard cell library. Hey, this is for this particular technology, like 24nm. Then you don't really need to design everything from scratch. You can make use of the standard cell library available and then you can design the chip. That works for the existing technology nodes. But if you're targeting the new technology node, obviously you have to follow the full custom design. Let's say we want to design chips for a particular application. We are working for a space research organization like ISRO. And there we want to design chip for a particular product like satellite. Obviously, we won't be looking at producing the chips in bulk. So we might prefer FPGA, field programmable gate array. Again, it depends on the complexity. In this case, it could be multi-million gate design, or even it might demand billions of transistors, but it's not going to be like 10 billion or 20 billion. It might be like 1 or 2 billion. Still, we would be able to implement the chip on FPGA. So FPGA is the good option if you want to produce specialized chips. We are not looking at producing chips in bulk. But you think of smartphone SoC. We want to produce millions of chips. Of course, the fabrication is going to be very expensive. But if you are planning to create millions of chips, then the cost per chip will be less. That's how ASIC works. This is the main difference between ASIC and FPGA. Whether you are going to implement the chip using either ASIC or FPGA, you should be familiar with the design flow. So in this module, I will walk you through the design flow, ASIC design flow. It's the superset of FPGA. Front-end design flow remains same. Whatever I'm going to explain as part of the ASIC design flow, front-end remains same from the spec to synthesis. But for the FPGA, what we do is we make use of the software provided by the vendor. For example, you are going to work with companies like Xilinx or Altera. They provide the implementation software. It takes care of the complete implementation. It's pretty much automated. But when it comes to ASIC, we need to decide whether it is going to be semi-custom or full custom. What if the chip has some kind of analog block, whether it's going to be analog mixed-signal design? That's what we are going to explore in this module. All right? This is how you can visualize the flow. It starts from specification. You need to understand how to deal with the spec. Then you need to understand how we create the architecture, and then how we create the functional model, then how we create the synthesizable RTL model, then how we verify the model, and how we synthesize it, and then how we insert the test logic. We follow a design methodology called DFT, design for testability. So from the spec to synthesis, including DFT, it falls under front end. And the remaining thing, from floor planning to GDS2, it falls under back end. It's called physical design. There we follow various steps. We create the floor plan, and then we place the macros, all the block subsystems, and then we implement the clock tree, and then we do routing. We perform static timing analysis, then we implement the layout, then finally we do DRC physical verification, and then we also verify the layout using layout versus schematic. The final netlist GDS. GDS means graphic design system. It represents the manufacturable layout. We share this routed netlist GDS2 with the founder. All right. Specification. How we define the spec. Experienced engineers like me, engineers with more than 20 to 30 years experience, we call them as architects. Architects define the specification. So they work closely with the marketing folks. Marketing folks interact with the consumers. They identify whether the consumers are happy and what kind of features they expect. So they define the new features to be included. They identify the requirements from the customer. And based on the input from the marketing team, architects define the specification. So to realize any electronic system, we need both hardware and software. So we partition the system into hardware and software. To realize hardware, we look at various options like ASIC, FPGA, PLD, or it could be standard chip. And whatever the chip we design, it goes as part of the board, motherboard. In parallel, the software programmers, they create the software, and then eventually the software will be running on the board. For example, you think of a smartphone, iPhone. It's based on the chip A17, SoC. So if you consider the motherboard, this SoC, it does almost everything for iPhone. Of course, there will be other chips, but we make sure that there are very few chips, and whatever the SoC we design, it helps us to reduce the size of the motherboard. That's the intention. And in this case, we are talking about smartphone SoC. In this case, we prefer ASIC, application-specific integrated circuit, because we are looking at producing millions of chips. If you want to produce chips in bulk, the best option is ASIC. So we look at like how to implement the chip, whether we can go with ASIC or FPGA, or we can also buy and use the standard chip. So there could be various options. And the software programmers, they create the software like system software that includes operating system and firmware. And then on top of it, we would be using various kinds of applications like mobile apps. That's how we can realize any system. So you always need to understand the system specification defined by the architects will be partitioned into hardware and software. And then they define the hardware specification and the software specification. We chip designers refer to the hardware specification. And then based on the complexity and based on the requirement, whether we want to produce chips in bulk, we decide whether it is going to be ASIC or FPGA. All right. For example, if you want to design a processor, then we should be familiar with instruction set architecture. This is RISC-V ISA, instruction set architecture. It explains everything. How many general purpose registers, how many CSRs, control status registers, whether we want to use base ISA, whether we want to use extensions, and whether we are going with machine ISA or supervisor ISA, what kind of processor we want to implement. That's what the specification explains. And we should be familiar with the instruction format and what kind of instructions, how many instructions, which base ISA we are looking at. That's how we deal with the spec. So specification is nothing but document. It includes all the details. What kind of chip we are planning to implement, inputs, outputs, waveforms, architecture, each block, the microarchitecture, subsystems, overall how many blocks would be there, how we are going to integrate all the blocks, what kind of bus, something like AMBA, advanced microcontroller bus architecture, maybe within AMBA, what kind of flavor, whether we want to use AXI or AHB, how we want to implement the SoC, system on a chip. So spec defines everything. For example, if it is going to use a particular processor, like a RISC-V, then we need to understand the instruction set architecture. So we need to refer to RISC-V specification, and the specification explains everything. Whether we are going to deal with base ISA, which particular base ISA, RB32i or RB64i or RB128i, and what kind of extensions we are planning to implement, and what kind of processor it is, whether we are planning to implement a microcontroller or desktop processor. If it is going to be a desktop processor, obviously we would be looking at various layers like machine ISA, supervisor ISA. So specification is a document. It includes all the details. It's going to be the golden reference for everyone. So architects define the specification. They partition the product specification into hardware specification and software specification. And what I'm explaining here, that's pretty much hardware specification. It explains everything about the chip that we want to implement. All right. Architecture. If it is going to be an SoC, system on a chip, or if it is going to be an embedded microcontroller, what would be the architecture? What kind of components involved? How many IPs are there? And how we are going to integrate all the IPs, all the subsystems? What kind of on-chip bus? That's what the architecture explains. So here, this SoC is based on various kinds of processor. For example, if you want to implement the CPU, then we need to understand the microarchitecture. If it is RISC-V, then how the processor is going to be, what kind of microarchitecture, then how to implement the processor as pipeline processor. All right, we are fine with the architecture. Then we need to create functional model, behavioral model. We refer to the design architecture and we create functional model. We prefer TLM, transaction level model, to realize the functional model. This is going to be golden reference for DUT. We use this functional model during simulation. This model is going to produce the expected values. Whatever the DUT we create, design under test or design under verification, basically it's a synthesizable model. You think about design, the goals are different. We think about power, performance, and area. We make sure that it is synthesizable, and we want to achieve power. We make sure that it consumes very low power. Performance, we make sure that we achieve our frequency. And then area, we make sure that it consumes very less area. We prefer HDLs, Verilog, or VHDL, primarily for DUT. It's completely different. When I say functional model, it's a transaction level model. It's going to process everything in terms of transactions. Transaction is nothing but packet. But you think of design, everything is going to happen in terms of binary. That's the main difference. Functional model is like software. It can do everything at the transaction level. So you can expect more performance. The purpose of TLM is to produce the expected value for the design. We can make use of this functional model during simulation, but the thing is, after creating the architecture, we want to make sure that the design can be implemented. Maybe we want to run the software on the functional model, and then we want to visualize how this product is going to be. Whether we can implement this particular hardware as chip, whether it can be implemented on ASIC or FPGA, whether it's going to be feasible, that's what we do with functional model. The first thing that we do is we create the functional model, and then we even run the software, and then we see like, okay, this is how the chip is going to be, and then we run the software, and then we want to see how the complete product is going to behave. All right, it's possible then, now let's create the synthesizable model. We will jump into design, right? And during simulation, what we do is, we instantiate the design in the test bench. When we provide stimulus to both design and TLM, the design will produce the output, the TLM will produce the expected value, and scoreboard is the component. It's going to compare the design output with the expected value. That's how we are going to verify the design. You need to understand this process. So architects create the design architecture. So they define the specification, hardware specification and software specification. And then the design architects, chip architects define the architecture. And then based on the architecture, engineers create the functional model. Companies may have different teams, like chip designers and software programmers, modeling engineers. So software programmers create the functional model, and they verify everything. We prefer functional models to verify the performance of the design. We also run the software and check whether the complete product works fine. That's what the modeling engineers would do. And then they make sure that this is going to be golden reference for the chip designers. In parallel, it's not going to happen sequentially. In parallel, the chip designers, they are going to write synthesizable model. Engineers like you might prefer languages like Verilog or VHDL. You implement the design. And then verification engineers, or you might be verifying your design. So in this case, during simulation, you will be making use of the functional model. The functional model will produce the expected values, and whatever the values you get from the DUT, basically you are going to compare the output from the design with the expected value, and that's how you are going to verify. All right. RTL coding. RTL means register transfer level. So whatever the design you implement using HDL, Verilog or VHDL, it will be synthesized as register transfer level logic. What it means is you can visualize the entire IP or subsystem or chip like RTL, register transfer level. It means the entire design will be like flip-flop, combinational logic and flip-flop. So it will be like multiple levels from input to output. You consider a chip from the input pin to output pin, you can visualize the entire chip like RTL, register transfer level logic. There could be multiple levels. Why RTL? Because it helps us to calculate the frequency. Here you can look at how we calculate the clock period. It includes clock to Q delay, propagation delay, and setup time. Every flip-flop has setup time, hold time, and clock to Q delay. Clock to Q delay is nothing but the propagation delay of the flip-flop. If the clock to Q delay is more than hold time, then obviously we consider clock to Q delay. So here, the clock period becomes like clock to Q delay plus propagation delay plus setup time. This is how we calculate the clock period. And from the clock period, we would be able to calculate the frequency. So once we implement the complete chip as RTL, we would be able to calculate the frequency of the chip. We prefer HDL. We have options like Verilog and VHDL. Both the languages are equally powerful. When it comes to creating synthesizable model, we look at two things mainly. One is the coding style, how we implement the logic. For example, we implement multiplexer, then we prefer case. Verilog provides a construct called case. Or if you are looking at implementing priority encoder, then we prefer if-else. So the coding style is important. Based on the style, the synthesizer will infer the hardware logic. Other important thing is synthesizable construct. We don't use all kinds of constructs for the design. The language provides constructs for design and constructs for verification. For verification, you can think of using all kinds of constructs. No problem. We are not going to synthesize the test bench. But when it comes to design, we have to think about synthesis. Synthesizer will not accept all kinds of constructs. Constructs like initial, while loop. We use them pretty much as part of test bench, not for the RTL. So you should be familiar with two things. One is synthesizable construct, subset. The other one is coding style. Now, synthesizable model is ready. We implemented the design. So we need to verify the functionality. Verification. Verification. We write test bench. We instantiate the design as part of the test bench. Test bench generates stimulus. It drives the stimulus. When the design produces outputs, the test bench collects the output and compares the output values with expected values. So we expect it to be kind of completely automated flow. This is how we try to verify the design. And the verification happens at different levels like block level, subsystem level, and chip level. We follow different methodologies for different things. We prefer white box verification for block level. We want to make sure that the block is verified completely, 100% verification. Theoretically, we can say 100%. Also, if the complexity is less, then we expect 100% verification. That's where we make use of random test cases. We want to find bugs very fast, and we want to make sure that we verify everything thoroughly. It's called white box verification. When it comes to verifying chip, we prefer black box verification. Just think about the implementation process. We make use of the pre-verified blocks for the chip. So we want to make sure that the chip works fine. So we would be looking at inputs and outputs, and we would be more interested in generating real-time scenarios. The chip is going to be complex, and the test cases will always be like directed test cases. They reflect the real-time scenarios. That's how the verification is going to be. It's called black box verification. We might also prefer gray box verification. It's the combination of white box and black box, especially to verify the subsystems. You think of subsystem, it makes use of 80% pre-verified blocks, and remaining 20% could be glue logic. That's the logic we implemented. So we want to verify the glue logic using white box, and the entire subsystem can be verified using black box. So it's called gray box verification. There could be different approaches. And you should be familiar with verification planning, how we create the plan for the entire verification process. For example, if it is going to be a complex SOC, then we need to identify how many pre-verified IPs would be there and how many subsystems we are going to implement. And after verifying everything, how we are going to verify the complete chip. Do we have functional models, pre-verified functional models? And can we make use of them to generate expected values? And what about the architecture of test bench? Look at here. Verification plan includes the architecture of the test bench. In reality, the test bench architecture is more complex than the design architecture. So it will have various components like generators, drivers, scoreboard. How are we going to make use of the existing functional models? How are we going to automate the simulation process? We don't want to verify everything manually. So verification plan is important. It will have all the details, how we are going to implement the verification flow. And you should also be familiar with the verification closure, how we are going to sign off the verification process. All right. We use various kinds of EDA tools for simulation. Take a look. We have written the RTL, synthesizable model, and then we have verified it. If there are any bugs in the design, then what we do is we update the designer, they update the RTL model, and then we rerun the simulation. So it's going to be like iterative process until we make sure that the design is perfect. We will not allow the design for synthesis. So once we make sure that the design is bug-free, then we approve the design for synthesis. So during synthesis, what we do, we convert the design into netlist. So if there is any RTL code, then the synthesizer is going to convert the RTL into netlist. It's going to make use of the technology library. It's based on the technology that we target. So it follows a process. It goes through various steps like translation, optimization, and mapping. So it translates into schematic, and then it optimizes the logic. We want to make sure that the delay is going to be small. We want to make sure that we achieve our target power performance and the area. That's where optimization is critical. The EDA tool is going to make use of its algorithm to optimize the design. And then finally, it maps the schematic using the technology library. And that's how the synthesizer is going to produce the netlist. Like this. This is the output of synthesizer. So synthesis is a process that converts the RTL code into netlist. There could be various synthesizers from EDA companies. Now, we need to verify the netlist. What if there is some kind of issue with the synthesizer? We are not sure whether synthesizer has produced the netlist properly. What if there are some bugs? So we have to verify the netlist. There are different kinds of options like simulation and equivalence checking. Mostly we prefer equivalence checking. Simulation means what we do is we replace the RTL by netlist. So we try to make use of the same test bench. Test bench is there. As part of the test bench, we instantiated the RTL and we have run the simulation. That's fine. Now what we do is we replace the RTL by netlist and then we will rerun the simulation. We make sure that we get the same flow. Whatever the netlist we produced from synthesis, we try to make use of it. We replace the design by netlist and then we rerun the simulation. We make sure that the design works fine. But the simulation is going to be very slow because now the design is implemented in terms of gates. So many things will happen in parallel. But the software has to execute everything sequentially, right? So it's going to really be very slow. That's where we make use of another methodology called equivalence checking. So we have equivalence checkers from EDA companies, different kinds of EDA tools. They are not like simulators. You don't really need to write any test bench. What the equivalence checker does is actually it is comparing the design with the netlist like this. So this is RTL, this is the netlist, and the equivalence checker is going to compare both. How? It will convert them into mathematical equations. In this case, you can visualize them like min terms or max terms. Whatever the RTL we defined, whatever the netlist we generated from synthesizer, the tool is going to generate equivalent mathematical equations like min terms or max terms. Then the tool is going to compare. If it finds any differences, it will highlight that particular portion. Hey, this is the particular component and it doesn't match with RTL. That's how we verify the netlist.